With that, I would like to invite Dr. Adi Pick, Head of Quantum Optics Theory Group, Institute of Applied Physics at the Hebrew University.
Thank you very much. Can you hear me well? Yes? Can you hear me well? Thank you very much. I want to thank the organizers for giving me the opportunity to speak at this conference. My name is Adi Pick, and I come from the Applied Physics Department at the Hebrew University, and I will talk about adiabatic quantum computation in open quantum systems. So first, let me say a word about adiabatic quantum computation. So this is a slightly different paradigm approach for quantum computation than the standard thing. So the standard quantum computer operates a little bit like a traditional computer in the sense that you take your qubits, your system, you initialize it, and then you perform a series of operations, quantum logic gates, and then you measure, and that's your computation. In an adiabatic quantum computation, you still prepare your system and you measure it in the end, but in between, you don't perform a set of operations, but you actually let the system evolve. Like a simulation, it evolves adiabatically, and this is the computation. And in principle, I'm interested in this kind of computation, which I think is very powerful for some specific problems. Today, I chose not to talk so much about algorithms, but about two theoretical aspects of adiabatic quantum computation. So let me just get to it. So I thought I will start by just saying what adiabatic evolution is. So basically, adiabatic systems are those that evolve adiabatically, meaning the following thing. So here's the adiabatic theorem. It says that if you have a system and it is slowly varying, it will remain in its instantaneous eigenstate as long as it varies slowly compared to the energy gap. So what that means is this. I wrote an equation on the board there. So in quantum mechanics, systems are described by a Hamiltonian. A Hamiltonian has eigenstates and eigenenergies. And if the Hamiltonian is time-dependent, so are its eigenstates. So if you look at this picture that shows the eigenenergies as a function of time, they change with time. But the theorem says the following thing. If these lines don't cross, if the system is gapped, then if you initialize your system in one of its states, say the green state, it will most likely remain in that state during the calculation or the algorithm. And the transition into other states, which is the computation error, that is proportional, inversely proportional to the energy gap. So that's the adiabatic theorem. It's great, but it holds for closed systems, or it assumes that the system is described by a Hamiltonian. But what we know is that the quantum systems that we want to use in order to build a quantum computer are not closed in the sense that they interact with our environment, and therefore they cannot be fully described in terms of a Hamiltonian, but they are what you call open quantum systems. So in the remaining part of the talk, I will talk about how to actually do things adiabatically for an open quantum system. So as I said, it's a theoretical talk. All right, so what's so special about open quantum systems? Open systems are not described by Hermitian Hamiltonians. So you can describe a system with an effective non-Hermitian Hamiltonian or a Lindblad operator, for those who know. But what's special about that? So Hermitian Hamiltonians have real eigenenergies, but a complex operator has a complex energies. And what that means is that this gap is actually complex. So you can ask now, what does it actually mean to evolve slow compared to an energy gap that is complex? And in fact, there are some substantial implications for adiabatic evolution. And I listed here two implications. The first is the following. You can have situations where you evolve things very slowly, and in principle, the adiabatic theorem should have hold, but it fails. And another thing that can happen relates to cyclic adiabatic protocols. So in a cyclic adiabatic protocol, you take a system and you change it in a cyclic manner. So you change its parameters from some initial state and back into the same initial state. And what normally happens in quantum mechanics is that the wave function of the system can acquire a phase. However, in an open quantum system, there are situations where the system will change, the state will change entirely, and I'll show you an example for that. So there are many things that can happen in open quantum systems, and today I will show you two special features of open quantum systems. So in the first part of the talk, I'll describe a protocol for quantum computation, which is an adiabatic protocol that uses the special properties of open quantum systems, and specifically exceptional points. And then in the second part, if time permits, I will talk about optimizing adiabatic protocols in open quantum systems, but also in general. All right, so the first part is more theoretical, the second is more applicative, and we'll see where I get. Okay, so, but to be specific, I wanted to give an example of the simplest adiabatic protocol, I think, and the protocol I want to choose is, I want to describe is, you take your system, say an atomic system, and you want to transfer population between the electronic states and do this adiabatically. So we can think about an atom as a two-level system, and we shine a laser at it in order to drive transitions, and the laser is described by its amplitude and frequency. So this system is described by a two-dimensional Hamiltonian, and let's think about the following protocol where we apply a pulse with a chirp. Okay, so the amplitude is just a pulse, and the frequency of the laser is swept through the atomic resonance. So in this protocol, I just can describe the system with a Hamiltonian, and I can find its eigenstates, and this is what I show there on the plot. I show the eigenvalues as a function of time, and you see that this system is gapped. So this means that if I initialize my system in the ground state, I will most likely stay in the ground state. And in that particular case, the ground state initially is the +1 eigenstate of the Pauli-Z operator. And in the end, it's the -1 eigenstate of the Pauli-Z operator. So this process brings you from state 0 to state 1. Great. So this is the deal for a closed system. And now I want to show you how that changes for an open system. So by saying open system, I mean that most atoms or electrons in atom can decay via, for example, the process of spontaneous emission. And we can model that in theory by adding a complex energy term that represents the decay rate. So here I wrote this -I gamma term where gamma represents the decay rate, and this Hamiltonian is non-Hermitian, but I can still diagonalize it and find the eigenvalues. And what you see here is we plot the real part of the eigenvalues again as a function of time. And when the decay rate is 0, then it's the same problem that we just solved. But now, as I introduce decay, the gap starts shrinking, and at some point it will close at a critical amount of decay, basically. And it closes at this very special point called exceptional point. So why is it special? It's special because at this point, the two-dimensional Hamiltonian has a single eigenvalue, but also a single eigenvector. And in fact, this is a point of non-analyticity. It's a branch point in the eigenvalue spectrum. And I'll show it has some topological properties. This is very related to the previous talk you've just heard. All right, so I just want to mention that this is not the end of the story. So this effective Hamiltonian description is valid under some severe assumptions of weak decay, but more generally, we describe atoms that interact with an environment with a Lindblad master equation, and you can ask, what are the exceptional points in the Lindblad picture? This is more abstract, the math is more involved, but for a two-level system, we can actually, we have a simpler description that is equivalent to the master equation, and we can describe two-level systems in terms of a three-dimensional vector called a block vector, and we can analyze the dynamics on the block sphere. So basically we can solve and show that the block vector evolves under this equation written over there, and we have this operator M, which generalizes the Hamiltonian. So now I'm showing you this because I want to show you the eigenvalues. So let's look at the eigenvalues of the effective Hamiltonian and of the Lindblad equation, and let's see what's the difference between them. So first of all, this block vector has this additional zero energy eigenstates, that's the steady state. But when we introduce loss, basically, we see that the gap closes in both the descriptions, in both the effective Hamiltonian approach and in the Lindblad approach, but the gap closes at very different points. So we see a different topology of the band closing points, and that matters for quantum computation. I'll try to convince you why. I just want to say that there's another way to look at this difference in the structure of degeneracies. What you see here, I plotted the distance between eigenvalues of the effective Hamiltonian. So when the distance is 0, it's a black point, and you see that the effective Hamiltonian has 2 points. But then if I look at the structure of degeneracies of the master equation, I get this bow-type shape. So I don't have any isolated points. And I want to try to show you why it matters. Okay, so I chose one protocol that actually relies on the geometry of degeneracies, and this is a cyclic adiabatic protocol. I already said the word, but I want to explain again what it is. So I want to give an example of a cyclic adiabatic protocol now. So let's consider once again the same system, an atom, a two-level system in an electromagnetic field, and I will take the parameters that describe the field, this frequency and amplitude, and I will change them along a loop in parameter space. So I just traverse the parameters along this red loop, and let's see what happens to the system. This is a cyclic adiabatic process if I do it slowly. So in one case, if my system does not have a degeneracy, if I perform a loop in parameter space, the wave function will return to itself in the end of the loop if it evolves adiabatically. But now if I encircle a degeneracy in the shape of this exceptional point, the exceptional point is a branch point in the spectrum. It's this square root thing, and if I plot it, I get this twist in the energy levels. So now if I traverse a loop in parameter space and I start from one branch, I will get to the second branch. And I have to encircle it twice to get back to the original point. So this is a different topology. It's interesting, but that's not even the end of the story, because what I showed you is how the state would change if I actually follow the instantaneous state, if I evolve adiabatically. But it turns out that I cannot evolve adiabatically in both directions. There's a chiral adiabatic condition, meaning that if I evolve adiabatically when I go clockwise, I cannot evolve adiabatically if I go counterclockwise. So there are very subtle points about open systems, and we thought it's interesting. We wanted to demonstrate it in an atomic system. I'm a theorist, but this was collaboration with a lab that has an NV center, which is a defect. Oh, you can't see this. It's a defect in diamond, basically. This defect has electronic degrees of freedom, and in the lab of Nir Bargil, my collaborator, they know how to drive excitations between the electronic states of the NV center, and they can monitor the population optically. And basically, we wanted to demonstrate this adiabatic protocol. We proved theoretically many things. So we showed that there are no isolated exceptional points in a two-level Lindbladian system, but we showed that you can find exceptional points in a higher level. So we could find isolated points, and we worked out a protocol that would do exactly what we want. I will skip this. And we could simulate it adiabatically, this switch that we wanted to show, but we couldn't measure it. And that's basically because we encountered an inherent challenge. If you want to evolve adiabatically around an exceptional point, there's an inherent challenge, because there's a trade-off between maintaining the coherence and maintaining adiabaticity. If you want to maintain coherence, you need to do things quickly, because systems decay. But if you want to be adiabatic, you need to do things slowly, because you want to be adiabatic. And in that system, we couldn't really find a sweet spot. So there is an inherent challenge, but there's also a technical challenge, and that is, how do we optimize adiabatic protocols? So now I will leave this exceptional point story and talk a little bit about optimizing adiabatic protocols. Okay, I have no idea how am I doing with time. 12 minutes, and I have 8 more. Great. Okay, so in the second part of the talk, I would leave this. So I'm still interested in open quantum systems, because the world is composed of open quantum systems, but now I will talk about optimizing adiabatic protocols. And basically, the regime we are interested in for technology is most usually very far away from these degeneracy points. If we want to do things adiabatically, we actually want gapped systems. So in the second part of the talk, I will still talk about adiabatic protocols, optimizing them, but away from degeneracies. All right, so I'll present 2 things if time permits, so an analytic optimization approach and a numerical optimization approach. And basically, I wanted to say here that we have seen now that adiabatic protocols are slow. That's a disadvantage for computation, but they're also very robust. I haven't said that, so they have an inherent robustness. Basically, in the pulse with a chirp that I showed you, the only thing that is important is that the detuning will go from very negative to very positive in order for the protocol to work. The details don't matter. So there's an inherent robustness, and that's why these protocols are so popular. So the question is it possible to relax the condition on slow evolution but maintain the robustness of the protocols? All right, so I want to show you first an analytic approach for spinning up adiabatic protocols. And the approach that I will present is something we call inertial control, and here's the idea. So it uses this pretty recent theorem that says the following thing. Say you have a system and it's not adiabatic, it's rapidly varying. Now, if you can find a basis transformation that transforms your rapid protocol into a slow and a gapped process, then, if the dynamics is adiabatic in the new basis, the system will get to the desired final state robustly also in the lab frame. So that's the idea. It's an abstract idea, so I want to give an example. It was introduced by my collaborators in this project, Roni Kozlov and Roy Dan from the Hebrew University. And here's an example for how it works. So let's consider the same example. A qubit, a two-level system in a rapid driving field, so the Hamiltonian is the same, but I didn't enforce any conditions on delta and omega. And now I want to find an inertial protocol. So I do the following thing. Instead of describing the dynamics in terms of the Pauli matrices, these sigma x, y, z, I will introduce new basis of operators, H, L, and C. H is the Hamiltonian, L and C are two additional operators that are orthogonal in some sense. And now I can find the dynamics. So basically, I use the Heisenberg equation, and I obtain this matrix equation where mu and theta are these parameters that I defined there. So why is this interesting? This mu parameter is something you can call the adiabaticity parameter. It's actually the rate of change of the parameters. So these delta dot and omega dot there are the rate of change of the frequency and amplitude of the field compared to the energy gap. This is the adiabaticity parameter. So to be adiabatic in the lab frame, this mu needs to be small. But what we see here is that in order to be adiabatic in this new basis, in the inertial frame, mu must only be slowly varying. Okay, so that's the trick. If I can find a basis transformation that would produce a new Hamiltonian that varies slowly, then maybe I don't need to be slow in order to be adiabatic or to be robust. So that's the idea. We heard about it, we thought it's very cool, and we wanted to try to take one of the known adiabatic protocols and find the inertial equivalent. So let me show you an example of that. All right, so the example I want to show you is of inertial, rapid, and robust single qubit gates. So our goal here was to improve an adiabatic protocol for a quantum logic gate, which I just wrote schematically as you take some input state for your qubit and you apply a gate and you get a final state. So we are searching in this project, we're searching for pulses that would simulate our U gate in the fastest and most robust way. And we will do it in an inertial protocol. So the protocols that we chose to improve are called adiabatic geometric gates. These are cyclic adiabatic protocols where the wave function acquires a geometric phase, and that phase determines the gate. And I will, again, it's abstract. I'll give an example. Here's an example of a geometric single qubit phase gate in a tripod system. So a tripod system, this just looks like a tripod. This is a four-level scheme, 4 levels of an atom, and we drive transitions between them. States 0 and 1 are the qubit states, and then we use the states E and 2 to basically perform our gate. So the protocol is the following thing. We actually do a adiabatic population transfer out of the qubit subspace and back into it. So we apply the set of pulses written in here. So it has 2 stages, the protocol. This is the first stage. We apply omega 1 and omega 2 to transfer population from state 1 into state 2. And then in the second stage, we bring the population back. Once again, we apply omega 1 and omega 2 in reverse order, but we change the phase of omega 2. And by doing that, the state 1 acquires a phase during the dynamics, and that translates into a relative phase in the between the qubit states. So this is a geometric phase gate, and normally it is performed with adiabatic pulses, but we found inertial pulses that perform this protocol. So basically we found shapes of pulses, omega 1 and omega 2, that can perform this protocol robustly. All right, so we did not constrain basically the slope of the curves, but their curvature. And what we find is this performance. So what you see here in this plot is the gate error as a function of protocol duration. And we compared standard adiabatic pulses. These are the blue and green lines with our inertial pulses. That's the red line, and you see that you get a smaller gate error for a given protocol duration. So this is nice, and with further optimization, we got even better results. But maybe the nicer thing about this scheme is the lower part of the plot, where we show that our inertial pulses are very robust. So in the lower plot, we actually we perturb the frequency of the laser. This delta represents the frequency. We perturb it from the desired operation point, and we see that this inertial pulse, the fidelity, the gate fidelity doesn't degrade, hardly degrades when we change the frequency by 30 megahertz to each direction. Okay, so we found we were interested with this, so we showed a particular energy level scheme that can implement these gates. All right. So I only have a few minutes. No, I'm out of time. So I will say that we're also working on improving numerically. So basically on designing optimization tools that once you give, so we do the standard optimal control thing. You send in a pulse to your system, you let it evolve, or you simulate it, you measure, you feed the result into a computer, and then the computer generates a new pulse that has improved performance. So we do this trick, and what we add into this story is that we add adiabatic constraints. So we're searching for pulses that specifically are best at being adiabatic, or follow the instantaneous eigenstate in the best way. And by doing that, and I'm skipping a little bit what's on the slide, but by doing this, we find, so we're trying to optimize, say, the blue pulse, where we start with a blue pulse and we look for an improved pulse that would have a higher fidelity and would also be robust. And what you see in red is the normal pulse you get with optimal control. It's kind of has a weird shape, and it's not so robust. Its fidelity degrades when I change the operation point from optimal. But then when we introduce these adiabatic constraints, we get a nicer looking pulse, and it's also more robust. And this is the kind of things we're working on. So I will say quickly what are the next steps. 2 minutes, great, now I have time. Okay, so where do we want to go with this? So we built up a set of tools, and I only showed you pretty important but simple problems of a single qubit phase gate, but we also performed entangling gates. We would like to now use these tools and improve adiabatic protocols that are being performed on larger systems. So this is, as you've heard in this talk earlier today, this is a very exciting time for atomic qubits. So there are amazing works from Quera and these startup companies in the US, and also labs where now they have hundreds of qubits, and soon they will have 10,000s. And on these systems of cold atoms in optical tweezers, for example, people demonstrated, and this year and last year, solving optimization problems also adiabatically. And the set of tools that I just showed you can be directly applied to these systems. So this is something we're working on. And we're also working on understanding the complexity of such problems. So complexity for a standard quantum algorithm is the number of operations you need to perform, or how it scales with problem size. For an adiabatic computation, the complexity is actually the running time, or how that scales with problem size. And since the running time is proportional to the gap, you want to know how the gap scales with problem size. So we're interested in understanding what's the complexity of the approach that I've just showed you. When we perform things faster than adiabatic, what is the complexity, or what is the computational power of these algorithms? So I just want to thank the people who did this work, my group. So I only showed the part of my group of the people that actually presented. My time is up. So I want to thank Jonathan and Daniel, who are sitting here and really contributed to the work that I presented, to my collaborators on the inertial gate project, and my collaborators on the Envy Center project. Thank you.
Thank you very much. Thank you. We have time for questions.
Hi, so thanks for this very nice talk. I have a question. I don't know how it's related. There was this work by Michael Berry, shortcut to adiabaticity by.
Yeah, they're related.
Yeah.
So
by
it's a different approach, yeah?
Yeah, because then it just needs. It doesn't need 4 levels, right? It just needs to tailor the pulse.
If you are relating, so there is a. I think the question is referring to this really wonderful paper by Michael Berry called Transitionless Driving. It was the beginning of a class of protocols called Shortcut to Adiabaticity, and also what I presented can be called Shortcut to Adiabaticity. It's different in the sense that what Michael Berry showed is he showed a construction of a Hamiltonian that is not adiabatic at all, but basically once you have an adiabatic protocol that you want to perform, he showed you how to add, to construct a new set of controls where the state will evolve according to the instantaneous eigenstate of the original problem. Yeah, it's a different way to speed up adiabatic protocols. Let's make it short. Yeah, we're aware of that. We're studying that as well.
Okay,
Yep.
thank you.
Okay, last question. We have a question here.
So what I showed here is a natural, so the question was about error mitigation and quantum error correction. So these are things you can do on top. So what I showed here is a way to do the calculation that should have a small error before you do any error mitigation or error correction. So this should lower, as you do things slower, or yeah, you reduce the single qubit gate prior to error correction.
Okay, thank you very much.